Hello. In this video, I'm going to give an example where we use a velocity versus time graph to construct the change in position of a train through some scenario. So here we have an example. The story or the narrative is as follows. There's a train. It leaves the station at time equals 0. That's convenient. And we'll just go ahead and say that that's x equals 0. That's our choice of reference point. And we will assume that it starts from rest. So starting from rest, the velocity increases steadily. We'll assume it's a steady increase to reach 5 meters per second over 2 seconds. So it takes 2 seconds and it steadily increases. We will assume that it maintains that same velocity, that velocity of 5 meters per second for 3 seconds. And then it will start braking. Think about what that means. After those 5 seconds, so 2 seconds to increase velocity, maintain it for 3 seconds, and then starting at time equals 5 seconds, it will come to a rest after 10 more seconds. So just so we're all kind of counting the time correctly, we would have 2 plus 3 plus 5, or sorry, we'd get 5, and then it comes to rest after 10 more seconds. So the total time for the whole thing would be 2 plus 3 plus 10, 15 seconds. Okay, so we want to analyze this, and our goal is going to be first to construct a velocity versus time graph, and then figure out the area under the curve for the whole 15 seconds, and that will give us the change in displacement. So we want to create the velocity versus time graph and create the change in displacement. How far did the train travel over those 15 seconds? So it's kind of a cooked up example, but all right. Now, we haven't done many problems yet this semester, so let's go through and kind of highlight important words. Train? No, doesn't matter. That's just part of the story. Important thing, though, we start at t equals 0, and this one might be important. It really is only going to be important if you want to know the absolute position, or as I said, let's find the displacement. But that might be important. So if I was reading this, I'd be kind of circling that in my mind. Okay, starting from rest. That's going to be a useful thing to note. Rest. If something is at rest, we know its velocity. If something is resting, its velocity is 0. Okay, so that's important. It starts from rest, so the velocity is 0 at the beginning. And then it increases to 5 meters per second, that's going to be important, and over a time interval, that's important. And then we're going to maintain. That means the velocity it maintains the velocity, so the velocity won't change over the next 3 seconds. These are all key words, so when you read a scenario like this, or in Sapling, when they give you a story, it's worth kind of going through and zeroing in on what are the key bits of information and what's just the fluff, just part of the narrative. It doesn't really matter. It could have been a car, it could have been a bicycle, it could have been a bug. I think it's happening. There'll be questions where it is a bug. All right, it doesn't matter. Something goes through this path, this set of stages. Okay, and then you start braking. Well, you know what happens when you hit the brakes, your velocity is going to, if you had a positive velocity, it's going to become less positive, okay? So, all right, kind of think about what that might mean for the graph, so that's important. And that happens starting at 5 seconds, and then it comes to a rest. Again, no, that's the same thing. Some of these keywords are the crucial ingredients to figuring out problems in physics. And then we have 10 more seconds. We want to find the total displacement in the whole time. All right, so let's go through this. We're going to make a graph of velocity versus time. I know that the whole trip takes 15 seconds, and I know the key points are going to occur so we're going to start at 0, and then 2, and then at 5 seconds, 2 plus 3, and then from then on. So, all right, so we're going to go ahead and I need 15 marks. So, let's see here. Well, if this is going to be 15, then half of that would be 7 and a half, so I'll call this 7. I call this 8, I guess. And half of that, a little bit less, 3. All right, so let's see if we can eyeball it here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That looks pretty good. All right, now go ahead and add the rest. All right. So I don't really care about all these times. Let's go ahead and just mark out the times that really matters. Something happens after 2 seconds. So that's going to be an important one. So we'll have 2 seconds. And then an additional 3 seconds. Well, that would be 2 plus 3. 1, 2, 3. That'd be 5 seconds. That's an important moment. So I want to kind of keep track of that one. And then for the next 10 seconds, well, that's going to be all the way to 15. Okay, so those are the key moments when stuff happens. You can add all the labels, but at some point, life is short. There's other stuff we want to do. But we do want to indicate the key moments in this narrative. Okay. Now, it starts from rest. So that means when time is 0, the velocity is 0. If it starts from rest, the velocity is 0 at time 0. I've been marking these points in green, so I'll just keep on trucking with that idea. So it starts at rest, at 0 velocity, and then after 2 seconds, the velocity is 5 meters per second. Well, so I'm going to go ahead and mark that here. And then I'm going to label the vertical axis, set a scale, and say that that is 5 meters per second. Okay, so after 5 meters per second, the velocity is 0. And we assume that it's steadily increasing. So we're going to assume that it just just increases linear. Oh, we'll assume it's just a linear increase over that interval, over the first 2 seconds. Next, over the next 3 seconds, the velocity is constant. It maintains it. So 3 seconds later, after 5 total seconds, the velocity should still be at 5 meters per second. So it'd be over here at 5 meters per second. It's flat because the velocity is being maintained. It wasn't changing. So it's a horizontal line. And then we know that after 5, when we get down to 15 total seconds or 10 additional seconds, the velocity is supposed to be 0. So I know the velocity over here is 0. Okay? So the velocity starts at 0, increases to 5, maintains 5, and is going to go down to 0 after 10 seconds. Well, I have to use a crutch here. I'm just not very good at this. Oh. So hopefully that's clear. All right. So that is the velocity versus time graph describing this story. So that's a really important skill to be able to read something and start piecing together graphs, and pretty soon we're going to have equations as well. Okay. Now, Great. So that was the first, that's half of what we were trying to do. Graph velocity versus time based upon the story. The last thing we were hoping to do was to find the change in displacement from beginning to end. And we can go back. We know that the slope of the position graph gives velocity, and the area under the velocity graph gives the change in position. So we want to use area here, not slope. We want to use area. So, all right, well, so I've got this shape. It's kind of complicated. It's a trapezoid. So some of you might remember the formula for a trapezoid. But if you don't, that's okay. We can just chop it up into 3 simple shapes. So rather than doing the formula for a trapezoid, think of it as like the average of the heights times the width, something like that. Instead, what we're going to do is break it up into, let's do some red, that's what I was doing last time, into a triangle plus a rectangle plus another triangle. And we all should know the formulas for the area of a triangle and a rectangle and another triangle. Okay? So let's do this in 3 stages. We'll find the separate areas, add them up, and we'll get our answer. So we're going to say the total displacement for the whole thing is the area of the triangle from 1 to 2 plus the rectangle from 2 to 3, no, 2 to 5, apologize, plus the triangle from time 5 to 15. Okay? 1 to 2, 2 to 5, 5 to 15. We just do them piece by piece by piece. So the area of a triangle from 1 to 2. Well, remember, the formula for the area of a triangle is 1/2 the base times the height. Easy enough. The base of this triangle is 2 seconds. And the height of this triangle is 5 meters per second. So that would simply be 1/2 the base of 2 seconds times the height of 5 meters per second. I'll watch my units. Seconds will cancel. That's good. I'm left with meters. That's really good because I'm trying to find a change in position or a displacement. So that should have units of meters. And I multiply these. This gives me 5. Meters. Right, let's move on to the next shape. 2 to 5 seconds, I have a rectangle. So the area of the rectangle from 2 to 5 seconds, well, the formula for a rectangle's area is just base times height. We have to get the right base and the right height. Okay? The base here is the width of the rectangle. It's only the rectangle that matters. That's actually just 3. 5 minus 2. That's the base. You don't go all the way back to 0 because you don't have a rectangle that goes all the way back to 0. The rectangle is just from 2 to 5 seconds for a width or a base of 3 seconds. The height is 5 seconds. So this is simply 3 seconds times 5 seconds. 5 meters per second. I apologize there. Misspoke. Again, units cancel. I'm left with just meters. That's good. And I get 3 times 5 is 15 meters. So it travels 5 meters here, and it travels 15 meters there. So it doesn't look quite right because I left such a gap between the shapes, but that is the right answer. Okay. And then I have to do the same process for the last triangle. So I have another triangle So I'm going to have a triangle from time 5 to time 15 seconds. Formula for a triangle is 1/2 the base times the height. The base in this case isn't 15, it's 10. 15 minus 5. The base of the triangle has length 10 seconds. The height is 5 seconds, or 5 meters per second. So I get 1/2 10 seconds times 5 meters per second equals half of 10 is 5, 5 times 5 is 25. So I get 25 meters per second. Very good. So I've determined all of the separate areas, and I can pull it all together to get the change in displacement over the whole 15 seconds is 5 plus 10, or 5 plus 15, that'd be 20, plus an additional 25, 45 meters. About half a football field. Okay? So that is how you can go from a narrative, a story, to construct a graph of velocity versus time. And then from that, as long as the shapes are pretty simple, and in this semester, that's all we will ever have. All of our motions will always be such that you can break up the velocity versus time graph into rectangles and triangles. We won't have things that are worse than that. And then you can get the total displacement by adding up all of the relevant areas under the curve. All right, thank you. In the next video, we are going to introduce a new concept called acceleration.